Hello everyone, welcome back to the channel. This is the last video for maximum power transfer theorem. I had already posted two videos on maximum power transfer theorem. If you haven't checked that, please check the link in the description box so that you can understand that what we mean by maximum power transfer theorem and how to calculate the value of load resistance for maximum power transfer, how to calculate the value of maximum power transfer to any load. Now, what we had seen in maximum power transfer theorem in the first video of this, that for maximum power transfer, the value of load resistance should be equal to source resistance, or this RL should be equal to RTH when we have a complicated circuit, which is usually the case. We normally don't have a single resistance in the circuit. And then the PL max is calculated using formula VTH square by 4 RTH. So what we had seen that we need to obtain the Thevenin equivalent of the network first, then we can apply maximum power transfer theorem. So if you have no idea that how to obtain the Thevenin equivalent, then you can check the videos of Thevenin's theorems. The link for the same is provided in the description box as well. Now in this video, I will consider the circuits where we will have the dependent sources present in the circuit in addition to the independent sources. We had already done in the Thevenin's theorem that RTH is calculated as ratio of open circuit voltage to short circuit current when we have a dependent source present in the network. So the same methodology will be adopted in this video as well. Now let's start with the first problem. First problem says for the network shown in figure, find the value of RL for maximum power transfer. Also calculate PL max, that is the maximum power transfer to the load. Now the network is having a dependent source. Polarity is marked, so it's a voltage source. Its value is 10I, so it's a current dependent voltage source. And here we have an independent voltage source of 50 volts. This one is 40 ohm. Current through this resistance is I, flowing in this direction, which is already marked in the problem. And this is RL. So these are actually the load terminals AB. Now since we have a dependent source present in the network, so we need to find out the value of RTH using VOC upon ISC. Also VTH is actually open circuit voltage. So firstly we will find out open circuit voltage, then we will find out short circuit current, then take their ratio to calculate RTH. For VOC, what we need to do, we need to open circuit the load terminals. So these terminals are open circuited. Now since the circuit is different from the circuit which is already present over here. So we will calculate the value of current in the circuit by replacing this current I by I1, because it's not same as I. So that will be reflected over here as I1. Now the current flowing in this closed path is actually I1. Let's mark the voltage drop polarities. And we can assign the voltage over here as VOC like this. I have considered terminal A as positive and B as negative. So we can find out VOC by applying KVL to this open loop, or even we can apply KVL to this open loop. There is no issue, we will get the same answer from both the cases. But firstly, let's find out the value of I1 by applying the KVL to this mesh, starting from this 10I source, 10I1 source minus 10I1 since negative sign came first, plus 20 I1 plus 40 I1 plus 50 equal to 0, which will give us the value of I1 as minus 1 ampere. Now for finding out VOC, if we apply KVL in this open loop, starting from this VOC minus VOC plus 40 I1 plus 50 equal to 0. So VOC is equal to 40 I1 plus 50. I1 is minus 1 minus 40 plus 50. So VOC is actually 10 volt. Even you will get the answer of this VOC same if you apply KVL to this open loop. Let's write that equation as well. So then minus 10 I1 plus 20 I1 plus VOC equal to 0. Minus sign minus 10 I1 plus sign plus 10 I1 plus sign plus VOC. So VOC will be equal to minus 10 I1, which is actually 10 volts. So whether you apply KVL to this side open loop or this open loop, it doesn't matter, answer is going to remain same. The next thing is we need to calculate the short circuit current. Now to calculate ISC, we need to replace the load resistance terminals by short circuit. This one is of 50 volts. This is 10I. Now since the circuit is again different from the initial case, this I, let's say, write it as IY, and it will be reflected over here as IY. Now in order to find out that what is the current through this branch, we need to apply mesh analysis. Nodal analysis is not applicable over here since we don't have any resistance in between these two. There is no potential difference, so we can't calculate the current like that. By using the nodal analysis, we need to apply mesh analysis. Let's say this, the current in this mesh is I1 and in this mesh is, sorry, not I1, let's say this is IX and this one is IY. Now we can assign the voltage drop polarity according to the two different currents. Apply KVL to first mesh and to second mesh. From mesh 1, what we have, minus 10 IY plus 20 Ix equal to 0. This is mesh 1 equation. Then mesh 2, 40 Iy plus 50 equal to 0. So Iy is minus 5 by 4 ampere. So once we have the value of Iy, then from first equation we can calculate the value of Ix as Iy by 2. So that will give us the value of Ix as minus 5 by 8 ampere. Isc is flowing in downward direction. This is the direction. So we need the resultant current in downward direction. So that will be from two mesh currents, Ix is in downward direction, Iy is in upward direction. So it's Ix minus Iy. Ix is minus 5 by 8, Iy is minus 5 by 4. So current through the short circuit is 5 by 8 amperes, which is actually 0.625 ampere. Now we have the value of open circuit voltage and we have the value of short circuit current. We can calculate the value of RL, which is going to be equal to RTH. And RTH is open circuit voltage upon short circuit current. The open circuit voltage was 10 volt, short circuit current 0.625. So RL is equal to RTH. It should be 16 ohms if we want to transfer maximum power to the load. Now the next part was that we need to calculate the value of PL max as well, which is given by VTH square upon 4 RTH. Now VTH is same as VOC 10 volts. So 10 square upon 4 into 16. PL max is 1.5625 watt. So we need to understand the importance of Thevenin and Norton's theorem, because if we don't know their procedure, then we can't even solve the problems of maximum power transfer theorem. So next problem is for the network shown in figure, find the value of RL for maximum power transfer. Also calculate maximum power. In this circuit, we have again a dependent voltage source. This resistance is a load resistance, 2 volts, 1 ampere, 1 ohm, 1 ohm. Voltage across this 1 ohm is Vx, and this Vx is controlling the voltage of this voltage source, which is supplying voltage to Vx. Again, we have a dependent voltage source over here. So in order to calculate RL, which is equal to RTH, we need to find out open circuit voltage and short circuit current, as RTH is given as VOC upon ISC. So VTH is same as VOC. So let's find out VOC first. followed by short circuit current. For VOC calculation, load resistance should be replaced by open circuit, means the load resistance is actually removed from the circuit because we have to find out the open circuit voltage across the load terminals. Let's say these are the terminals assigned as positive and negative. 2 volts, 1 ohm, 1 ohm, and here we have a voltage dependent voltage source. Now the circuit configuration is different, so I will write this Vx as Vx1 and that will be reflected over here. We need to find out the voltage VOC. Now how can we find out VOC? That we can find out that if we know that what is the voltage across this branch, then we can apply KVL in this loop. Let's say this voltage is V. Then we can write, like we can say this terminal is negative and this one is positive. So we have minus V minus 2 plus VOC equal to 0. So VOC is equal to V plus 2. So we need the value of voltage V. Now how to find out voltage V? That can be found with the help of applying KCL over here. Now for KCL, from this side 1 ampere current is incoming. For this side, let's say for this branch, since the current direction is unknown, I'm assuming this one is outgoing, and in this branch current is actually 0. So this 1 ampere should be equal to current flowing through this 1 ohm resistance which is connected in series with this 2 Vx1 voltage source. So 1 is equal to V minus 2Vx by 1. And we have one more equation. We need to find out that what's the value of this Vx1. Now what is this Vx1? Vx1 is actually voltage drop across this 1 ohm. So it is 1 into current through this 1 ohm in this direction only, since this terminal is positive, this one is negative. So current in this is V minus 2 Vx1 by 1. So from here what we get that V is equals to 3 times Vx1. Now substituting this value of V in this, we will have the value of Vx1. Let's say in this equation, so where 1 is equal to V minus 2 Vx1, we have calculated that V and Vx1 are related by relation. Yes. So Vx1 is actually 1 volt. So when Vx1 is 1 volt, then V is 3 volts. V is 3, but our question was to find out VOC, for which we had already written that VOC is equal to V plus 2. So VOC is equal to V plus 2 equal to 5 volts. The open circuit voltage is 5 volt. Second is we need to find out short circuit current. For short circuit current, the load terminals, these two terminals, they should be replaced by short circuit. Here we have 2 volt source. RL terminals should be replaced by short circuit, and we need to find out the current over here. Here we have a resistance in series with the current source, 1 ohm, 1 ampere, 1 ohm plus minus Vx, and this one is plus minus 2 times Vx. Now again the circuit is different from the initial circuit. So Vx is different from the initial case. Let's write this is Vx2, and same will be reflected over here as Vx2. Now we need to find out the current ISC. Now in this case, we can't find out the current in this branch by finding out the potential difference divided by resistance. Since the resistance of this short circuit is 0, that means infinite current, which is not practically true. So we need to go with the another method with which we can find out the current through this branch. So the most suitable method is actually mesh analysis. For that, I am assigning current I1 to this mesh and I2 to the second mesh. So as per the flow of I1, the voltage drop polarity across I1 1 ohm is like this, and across this 1 ohm is like this. Now when we try to apply KVL to mesh 1, what we see that we have a current source over here. So when we have a current source, we don't know that what is the voltage drop across that. Then we need to combine these two meshes, mesh 1 and 2, to form a super mesh. So here we need to apply KVL in this super mesh. So when we apply KVL to the super mesh, starting from this source, minus 2 Vx2 plus 1 into I1 minus 2 equal to 0. This is one equation. Second equation is the constraint equation. Now the constraint is that is the resultant current through this branch should be 1 ampere and it should be in upward direction. I2 is flowing in upward direction, I1 is in downward direction. So I2 minus I1 should be 1. Also ISC is same as I2. So if we know what's the value of I2, then we can have the value of ISC. So I2 is equal to 1 plus I1. We need the value of I1. We have just one equation over here, that is minus 2 Vx2 plus I1 minus 2 equal to 0. Now we need the value of Vx2. For finding out Vx2, now this Vx2 is the voltage drop across 1 ohm resistance. Current is flowing in this direction. So as per this flow of direction, this terminal of 1 ohm resistance should be positive and this should be negative. So drop magnitude is 1 into I1, but the polarity of Vx2, which is already given, that is just opposite to what we had assumed. So it will be minus 1 into I1. Now let's use this value of Vx2 in this equation. So it will become 2 times I1 plus I1 equal to 2, or I1 is 2 by 3 ampere. So when I1 is 2 by 3 ampere, then I2, which is equal to 1 plus I1, it's 5 by 3 ampere. I1 is 5 by 3. RTH, which is ratio of VOC and ISC. Now this is same as ISC. I2 and ISC both are same. I2 ISC. VOC is 5.5 by 3. RTH is actually 3 ohm. PL max is, which is VTH square by 4 RTH, 5 square by 4 into 3. It's 2.083 watt. So last problem which I am considering in this video and also for the maximum power transfer theorem is, what will be the value of RL to get maximum power delivered to it. What is the value of this power? The circuit is a 3 ampere source in parallel with 4 ohm resistance. Here we have a voltage dependent voltage source, another 4 ohm resistance, resistance RL, and voltage across this is V. This is not V1, this is actually V. 0.5 V. So V is the voltage across the load resistance. Again, due to presence of this dependent source, we need to find out the value of RTH as ratio of open circuit voltage to short circuit current. VTH is same as VOC. So we need to find out open circuit voltage as well as short circuit current. For VOC, the circuit will remain as it is. The only difference is that the load resistance should be removed from the circuit. Since it's different from the earlier one, we have removed this one. So it's voltage V1, and that has to be reflected over here as 0.5 V1 with this terminal negative and this one as positive. Now we need to find out this value V1 because V1 is same as VOC. VOC and V1 are same. So if we find out the voltage across this 4 ohm resistance, then we can find out the VOC. For that, what we can do, we can actually apply source transformation over here. So when we apply source transformation, it will become very simple circuit. The 4 ohm resistance will be connected in series with the voltage source. Now voltage source will have value 3 into 4, 12 volt. Arrowhead replaced by positive terminal, arrow tail by negative. Four ohm, and this one is voltage V1. Now it's very simple problem. Let's say current is I. So V1 is equal to 4 into I. This terminal is positive, this one is negative as per direction of I. Same polarity. So V1 is 4 into I. We can apply KVL starting from 12 volt minus 12 plus 4I minus 0.5 V1 plus 4I equal to 0. Now 4I is equal to V1. So minus 12 plus V1 minus 0.5 V1 plus V1 equal to 0. So 1.5 V1 equal to 12 and V1 is 8 volts, which is actually VOC. So one current source transformation simplified our circuit to a simple series circuit. Second one is for calculation of ISC. The circuit will remain same with only difference that the load resistance terminal should be replaced by a short circuit. So in this circuit the only change will be that these two terminals will be replaced by short circuit, rest of the circuit will remain same. 4 ohm. So here we will have short circuit, 4 ohm, 3 ampere. Across this short circuit, let's say the voltage is V2 instead of V1 or V. Now it's different because this is now short circuit. Earlier it was an open circuit when it was V1, and in the initial circuit its voltage V, which is across resistance RL. So that differentiation is marked by assigning this voltage as V2, and this will be reflected over here as V2. Now this V2 is the voltage across the short circuit. Across short circuit, voltage is always 0, because what is voltage? Voltage is current into resistance. The resistance of the short circuit is 0, so across the voltage short circuit voltage is 0. So V2 is 0. When V2 is 0, it means this source is not supplying any voltage. So this source will get eliminated from the circuit. Then this 4 ohm is in parallel with the short circuit. Any resistance which is in parallel with the short circuit, that will get actually short circuited. Through this the current is ISC. Now again this 4 ohm is in parallel with the short circuit. So this will also get eliminated. So what is left? That ISC is directly 3 amperes. We don't need to do any calculation. The circuit is simplified to this, that whole current flows through the short circuit only. ISC is 3 ampere. Then we have to calculate RTH, which is VOC upon ISC. It's 8 by 3, which is 2.667 ohm. PL max VTH square by 4 RTH. VTH is 8 to 2.667. So which gives us the value of PL max as 6 watt. Now I hope that these problems are sufficient enough to understand the maximum power transfer theorem. If you find these videos useful, please consider subscribing the channel. Thanks for watching the video.